All right, it looks like we have a couple people still trickling in, but before we get started, I do want to talk about how we'll be going through a problem today, a problem that won't be unlike a problem you might see on an exam, similar to problems that you'll do in the homework for this week. So if you want to follow along with that in more than just sort of the slides that we'll do, you're certainly welcome to go to the starter sheet, which is in the week 4 content. So if I click on week 4 content here, you should be able to see it. This is lecture 11 starter sheet. If you click on that, then you'll get this form here. There also is an asynchronous video of me doing this problem online through the website. So if you go into week 4 and you click on here in the non-live portion, if you click on lecture 11 here, then this is a YouTube link of me doing this problem as well. Now, before we get into the lecture today, we did talk last class about how we have an exam coming up. So it is currently June the 8th, right? So that's here, we're on this Monday. We will have the exam next Tuesday. So it will cover all the material we've covered up to this point, plus on Wednesday we'll do a bit of a review and we'll do a problem similar to the problem that we'll do, but where the working fluid is an ideal gas instead of water. So we'll run the exam next Tuesday. That'll give you a chance to go through the quiz for this week and the homework for this week. So both of those things are related to this exam, and doing them will help you study. So the layout of the exam will be 10 multiple choice questions that we will run through a quiz on my courses. There will be 2 long answer problems. These will be like the homework problems. I'll set up a document online where you can access that document. You can work on that problem in whatever paper that you like. You scan it, upload it as a PDF to a Dropbox that I'll create specifically for that exam. If you have any problems with uploading or anything, I'll provide a email address where you can contact me and a cell phone number as well. Access to both parts will run on Tuesday from 3 p.m. to 7 p.m. Eastern Time. So that gives you 4 hours. That's more than twice the length that we normally would give for an in-person exam. So you should really have a lot of time to kind of, to make sure that you can access the materials, print them out if you have a printer, or access them through the computer as you're doing the exam. It will also give you time to upload your materials while you're, when you're finished working on the exam. I will run a meeting on this same link that we use for office hours and for courses from 5:15 p.m. to 7 p.m. during this exam, so that if you have problems, just like if you had problems during a normal exam, you'd be able to put your hand up. So, if you're there, I would ask you to mute yourself. So don't ask questions verbally, but to send questions through the chat. You can either send them to everyone, or if you click down, if you have the chat function open here, you can see when you're chatting, you can send something to everyone, or you can send something to a particular person that's in the meeting. So you can do that either way. And if you have approved accommodations from the university in terms of the length of time that you have to write an exam, we will honor those accommodations, and it would be at your discretion whether you'd like to either start a little bit earlier or end a little bit later. So those are the pieces of information that I had about the exam. Does anyone have other questions about how the exam will be delivered? Doesn't sound like it, so we'll move on here. So I guess the other thing here, right, so I think that among other faculty members, there's been some concern about academic honesty on, it looks like maybe we have something in the chat here. Will we have access to the full 4 hours? Yeah, so you'll have access for the full 4 hours. There won't be a timer based on when you initially. So it's not like you only get 2 of the 4 hours. So you'll have the exam, you'll be able to access it right at the beginning of the time, and the Dropbox will close at the end of the time. Well, probably more like 15 minutes after the end of the time. So you won't be timed. There'll be no penalty for using the whole time, or no bonus for using less than all of the time. Any other questions? So I guess the other thing is just that I would, so for this exam, I'll be treating you like an engineer, which means that I'll trust you to act ethically. We got to treat this exam in the same way that we would treat an exam that happens on campus in a room where, we're limited to the exam materials that we're given. So I will provide tables for you to look materials up. I will provide the questions that you need. So everything that you need will be in the downloadable packet. Or on the multiple choice questions themselves. So you shouldn't need to access any other material through the internet, except potentially this Zoom meeting if you'd like to ask questions. If you do have any questions or conflicts with the exam time, please let me know and we'll find something that works for everybody. Are there any other questions about the exam before we get started on today's material? All right, so today we're going to continue our look at the first law of thermodynamics for closed systems. So as the exam is getting closer, we're getting close to wrapping up the material that we need to do on closed systems. And actually, we won't have any new material. So we have our lecture today, which is going to go through an example of a multi-step first law problem in a closed system. And then our lecture on Wednesday will be a review of all this material that we've done for closed systems. Plus, we'll do another example where the working fluid is an ideal gas. Remember, one of the key questions that we need to ask is kind of what's the fluid in our system? So our approach will be different if it's something that goes through a phase change like water, or if it's an ideal gas, maybe like air, right? So this problem, or this lecture, will deal again with the first law of thermodynamics. And we're going to do this problem. Again, you can access the starter sheet for this problem on the My Courses webpage. It's the Lecture 11 starter sheet. So here we have 2 kilograms of pure water, and it's held in a piston cylinder assembly like this one shown here. The water initially exists at 1 atmosphere and 20 degrees Celsius. It is heated at constant pressure until the pistons hit the stops. So we have this original length here, and then after a certain amount of time, we expand, and then eventually we hit these stops over here, right? So that's when our first process ends. But as we move from that position 1 to position 2, the first part, that all happens at constant pressure. Then we're told that heat addition continues until the water reaches 4 bar. So the pressure keeps going up, because now what happens, this is like, I made my kids some oatmeal today in our pressure cooker. We have one of these Instant Pot deals, right? Like an electric pressure cooker. And what happens is, you heat up the water and the oats, they're in there, and it's, the water gets hotter and hotter, but eventually it starts to form water vapor. And then as that happens, the increase in pressure in the vessel, clicks close this valve. And then what happens is you start to add heat and you get this higher pressure, right? And we know that that changes the saturation temperature of water. The boiling temperature of water goes up as the pressure goes up, right? So that's what's going to happen here. And we're asked to find the total work and the total heat transfer of both processes. And we're asked to sketch this 2-part process, or these 2 processes, on a TV and a PV diagram. So I think all of these skills are going to be important for you as you prepare for the exam. You're going to have to know how to manipulate the first law, find things like work, heat, and delta U. But you're also going to have to know how to sketch these TV and PV diagrams. So I'll show you how we're doing that in this particular problem. Now this problem, I don't know if you're ever interested, but when you graduate, you'll be able to sit for the FE exam. So if you ever want to, I guess it's part of the legal definition of being an engineer, right? So if you want to, you may have heard that engineers have the ability to kind of stamp things, right? So that's kind of giving your seal of approval as a professional engineer that a particular thing is safe or meets some safety requirements. So in order to get one of those stamps or one of those seals, you need to go through this kind of accreditation process that's beyond what you do in the classroom at RIT. So you'd sit for another exam, and then there's some experience requirements that are involved with that too. So one of the exam that you sit for kind of has a small book that comes with it that sort of reference material for anything in engineering, right? In mechanical engineering. And these are the tables from that exam. So you might see tables like this on the exam, and they're a little bit on that PE exam, right? It's a little different than the tables that you see in the textbook, but ultimately it's the same thing. So this is for steam tables for saturated water. So it means that we're somewhere between saturated liquid water and saturated vapor, right? So these are our two-phase tables. This looks the same as the one in the textbook where temperature is on the left-hand side, and you have nice round numbers for temperature, and then it tells you the pressure that water boils at for each one of these temperatures. Then you have things like specific volume, specific internal energy, specific enthalpy, and specific entropy. We also have tables for superheated water vapor, right? So here, this is particularly, we've cut out or snipped out parts that are at 0.4 megapascals. 0.4 megapascals is the same as 4 bar, right? Because 1 bar is 100 kilopascals. 1 megapascal is 1,000 kilopascals. So if you take 1 megapascal is 10 bar, or 1 bar is 0.1 megapascal, right? Because it's like 100 versus 1,000, right? So this is what we'll need for state 3 in our system. We're also given some information about specific heat and density for mercury, ammonia, and water in case we need that information as well. So the first part of our solution process is what's the given information. So in this case, we're told the piston geometry. We're given a diameter, which to me means that the cross-section of this piston is a circle, right? It has 1 diameter, so we should be able to find the cross-sectional area if we need that, right? Or the volume, right? Which would be that cross-sectional area times some length. State 1, we're told the pressure and the temperature. State 2, we're told the position of the piston. We're told in state 3 what the pressure is. We're required to find the total work. That's the work in the first process from 1 to 2, plus the work in the second process from 2 to 3. We're asked to find the total heat transfer, which again will be the sum of these two processes. And then we're asked to sketch TV and PV diagrams. So the next part of our solution process is to draw the schematic, right? So the schematic is given in the problem where we have this piston cylinder assembly, and we start at some distance, we're adding heat, so this water eventually begins to change phase and then expand, and we end at this L2, and the piston stays in the same position for that whole process from state 2 to state 3. We're also given these nice to-scale TV and PV diagrams. If you're doing this on a test and you're not given things to scale, that's fine. You just you can draw it out as a sketch, right? And you just have to recognize that when you're sketching it out, if you're trying to get some information, you're not necessarily sure what phase you're going to be in by your drawing because your drawing will have some inaccuracy. We know this first process happens at constant pressure because the problem told us. We know that the second process happens at constant volume because the first part, state 2 in my process, the piston here is at these stops. State 3, the piston stays on the stops because that pressure, it keeps expanding, right? We're creating more and more vapor, so the piston doesn't move inward. We also know that the mass is constant. So this is a bit tricky and maybe not immediately obvious, right? So here, if I move from state 2 to state 3, and the volume stays constant, right? Now I have a constant mass, right? Because this is a closed system. So because little v, or specific volume, is the volume divided by the mass, when the volume stays constant in a closed system, the mass is also constant. So v is constant, big V is constant, m is constant. So that means big V divided by m, that's the specific volume, is also constant. Right? So here we know V1, we know the mass we're given, and I can't remember if we're given the mass, but maybe we can find it. But here we know the volume and we know the specific volume, or at least we might be able to find it given the information that we have. The next step is to look at our governing equations, right? So in this case, if you don't know what your governing equation is in this class, guess that at least one of your governing equations is going to be the first law of thermodynamics. It's the most important law in thermodynamics, the most important equation, right? So if you don't know what to do, try conserving energy, right? We're going to neglect kinetic energy, potential energy, or spring energy. So we're going to assume that spring energy part means that the sort of like increase in pressure inside of our system isn't, elastically deforming our piston cylinder assembly a lot, right? So there's not some extra spring energy stored in that piston cylinder assembly. We do those assumptions because then our delta E term becomes the change in internal energy, right? And that's good because that means we can look up specific internal energies as long as we know the mass, then we can find delta big U. When we have this equation for closed systems, we know that we could find work if we have pressure as a function of volume. We know that if we have enough information to fix our states, then we can find the change in the specific internal energy and multiply that by the mass. And then usually we'll have to do those two things separately and then find the amount of heat that's transferred either into or out of the system. Now it's important to remember in this case, we think, right, that we're adding heat to boil this water, and that's what's making the liquid water expand. So because of that, we're expecting Q to be positive, right? Because heat in is positive, right? We can remember that mnemonic device, hip to win, right? So if heat in is positive, then we would expect, in this case, to have a positive value of Q. So here what we do between these two slides. So this is true for the process between state 1 and state 2, but it's also true for the process between state 2 and state 3. So we're going to use the first law, and it's such a great equation that we're going to use it twice in this problem. Once from state 1 to state 2 for that first process, and again from state 2 to state 3. I'm going to advise you on your exam, if you have a problem that has more than one state in it, and you will, I think you should write out at least a state table, right? So that's up here. Maybe you don't need the process table, although I think that's also sort of useful for accounting for different pieces of information, but you almost need to be writing out state tables, right? It's possible to do the problem without them, but they're very helpful. Right? And the nice thing about this is here, when I look at this problem, I know right off the bat, or at least I'm hoping, that I might be able to fix state 1 because I have two independent properties. They're temperature and pressure, so it's possible that they're dependent and not independent, but I know that that's a place where I can start. The other thing that I know, which might make me a little bit worried, is that I don't have two intensive properties for state 2 and state 3. I'm only told the pressure at state 2 and state 3. But I'm kind of hopeful because in the problem I can find the volume. So I'm kind of hopeful I might be able to use that information to find the specific volume as well. So just from looking at my state table, I'm kind of thinking that when I start to get numbers for my states, maybe I can look at volumes. Now, there's always kind of two, right? We talked about how this class, these problems in thermo are a bit like a choose your own adventure, right? So is the system open or closed? What's the fluid? What happens to the energy, right? Now, that's part of what you're doing. Another big decision that you're going to have to make is, should I do the whole problem symbolically to get equations and then fix the states at the end to get numbers? And that's, or I guess the other option is, I got this state table, let me fill in all the information that I need on the state table, right? So my advice is always going to be, do the problem symbolically first, right? We have these equations, keep everything as variables, go through till you get equations that tell you what properties you need. Because maybe you don't need all the properties that are on your state table, depending on how you construct your state table. And if you spend a lot of time finding, like, for example, if a state table here had not just specific internal energy, but maybe specific enthalpy or specific entropy as well, you might spend a lot of time filling out those parts of your state table. And then you get to the equations and you realize you don't even need that information, right? So my advice is going to be, figure it out symbolically first, and then fix the pieces of information that you need to do your equations. So I'm hoping that I'll be able to find specific volume in these cases, right? Because I know something about the volume, right? So I know that L2 here is 1 meter. And I know that L1, well, actually, it doesn't look like I know L1, right? So I know L2 is 1 meter, and I know that the diameter is 2 meters, right? So here, if I do this volume, right? So this is nice, mathematically, I can kind of do this in my head. Because if the diameter is 2 meters, then the radius is 1 meter. 1 meter squared is just 1. L2 is 1. Pi is 3.14, or close enough. So I can see that my volume at state 2, which is the same as my volume at state 3, is going to be 3.14 meters cubed. So I know from what I wrote before that the specific volume at state 2 is equal to the specific volume at state 3, which would be equal to this V, which is V2 or V3, divided by the mass. So it looks like maybe the problem did give me the mass. Let's go back and look at the actual problem statement here. Yeah, so they told me that it's 2 kilograms. So in this case, I didn't have to figure out the mass. So because here I knew the mass, now I can fill this in, and I know that V2 is equal to V3, which is 1.57 cubic meters per kilogram. So now I can put this in, and at least I feel like, I'm not going to solve all the rest of the stuff. I'm not going to do a bunch of linear interpolation, but I feel like from here, I could at least fix all these states as long as this state 1 is not under the vapor dome. And because I've spent my entire life here on Earth, where the pressure is usually around 1 bar, I know that water boils at a temperature that's going to be higher than 20 degrees Celsius, right? Usually right around 100 degrees Celsius. So I feel pretty confident that this is not under the vapor dome. In this case, pressure and specific volume, those two things are always going to be independent. So I feel like even if I don't do the math yet, I can fix all 3 of these states, right? So now I want to figure out where each state is on my vapor dome, right? Because one of the skills that I need for this exam is, how do I draw these TV and PV diagrams? So the first thing that I want to do, I like to do the TV graphs first, because to me they make more sense, where this pressure is moving up from left to right, except that it's flat under the vapor dome. Now this one's to scale, so I know that at 1 atmosphere, water boils at 100 degrees, so I know where to put this, at least the flat part under the curve, and then I'm sort of guessing about the slopes here. The slope in the subcooled liquid region is very, very steep, and the slope in the superheated vapor region will be, somewhat less pronounced. So I know my state 1 is at 20 degrees. 20 degrees is less than 100 degrees, right? So it's going to intercept my constant pressure line here in the subcooled liquid region, right? Because it's below the saturation temperature. So I know that state 1 is going to be a subcooled liquid. State 2, it tells me that the specific volume was 1.57. Well, it doesn't tell me that. I figured that out myself, right? So here, this is a log plot. I'm just guessing where this line goes. I don't know exactly if it's just at the edge of this two-phase region or maybe over here in the superheated region. But I'm going to just draw it here. But this is one of those cases where, particularly if I was drawing this freehand, I really wouldn't know where to put this line. And I wouldn't know if this is two-phase or not. But I'm going to show this as two-phase. Right? Oh, here it looks like in the table, I could look this up. So I can look up what VG is for a temperature of 100 degrees or a pressure of 1 atmosphere, depending on the tables that I have. And here I see that it's 1.67. And because I'm 1.57, then I'm to the left here, right? So VF, probably about 1 over 1,000 over here. VG on the red line is 1.67. Turns out I'm a little less than 1.67, so I should definitely be under the vapor dome here. But if I didn't have that information, I would still just sketch it out. And if on a test, if you're sketching it out before you really know exactly what's happening and you put it in the wrong place, I think you're still trying to show just a thought process of how you do it. So it's not necessarily did you get it in the right place. It's are you sort of demonstrating that you understand how to construct these particular graphs. So here we know that state 2 is two-phase. Now, what we know about state 3 is it has the same volume, and because the mass is constant, then that means it has the same specific volume. So now it's going to be somewhere on this purple line, this vertical line here, and the pressure is 4 bar. 4 bar is bigger than 1 atmosphere, which is right around 1 bar. So now I'm going to draw another constant pressure curve, right? So again, it slopes up from left to right, and it's flat under the vapor dome, but it's higher here, right? So then my state 3 has to be somewhere up there as a superheated vapor. So that's how I go through and draw my state table, or my TV diagram, right? So we know that V2 is equal to V3, which is 1.57. The PV diagrams, for me, I find they're a little bit trickier, right? Because the constant temperature lines here are going to slope down as we go from left to right, right? So here, I know that initially I'm talking about 1 atmosphere, right? And here, just for context, I'm drawing this 100-degree line here, right? So this would be saturated liquid at 100 degrees. But state 1 is 20 degrees, right? So what would happen is if we drew a 20-degree line, it would slide down here. So it would have some constant pressure line down here, and it would come up through here. So because we're at 20 degrees, it has to be below this 100-degree line. So I'm going to draw it over here because we know that the pressure is 1 atmosphere. So we're going to draw it over here. We know that, again, we have a specific volume that's less than the specific volume of the saturated vapor. So we're going to be close to, but not at the saturated vapor line. And then here, we're going to be up at 4 bar, so the pressure is going to go up, and we draw this over here, right? So again, we're in the superheated vapor region over here. So this is from state 1 to state 2, some constant pressure. From state 2 to state 3, some constant volume. So I don't even know what the numbers are, but at least I've drawn sketches of what the PV and TV diagrams look like. So now I'm going to try to go through some symbolic solutions here, right? So the first thing that it asked me to do is find the total work. So I know the total work is the sum of the work in the first process with the sum of the work in the second process. I know that to find work, I have to take the integral of P dV. In this case, it's the work from state 1 to state 2. So here, this is nice because I know the pressure is constant. So if the pressure is constant, it comes out of the integral. And the work here is just P times delta V. So I might have known that just from drawing my PV diagram. That's why these PV diagrams are useful, because if you have this PV diagram, you can just take the area under your process line to find the work. And here I had a constant pressure, so it's just a rectangle, right? So it's P times delta V, or pressure times mass times V2 minus V1. Here, I don't know the work. I do know the pressure. I do know the mass. I do know V2. And I don't know specific volume of 1. So I was close, but not quite. So how do I find the specific volume at state 1? So state 1 is a subcooled liquid. And for subcooled liquids, we will approximate every property by assuming that the property of the subcooled liquid is approximately equal to the property of a saturated liquid with the same temperature. So here, my temperature is 20 degrees. I'm going to assume this specific volume is the same specific volume for water that was boiling at 20 degrees at whatever low pressure that is, right? So here I look it up on the table, and it's about 1 over 1,000, because specific volumes for liquid water, it's almost always right about 1 over 1,000. So on these tables, I think for this problem, they're nice. They don't do that multiply by 1,000 thing. But you always got to remember that if you're talking about a subcooled liquid, your specific volume should be right around 1 over 1,000. So now I know all the pieces of information for this equation for the work from state 1 to state 2. So I can put all this information in here. I know that the pressure is 101.3 kilonewtons per meter squared, right? Which is the same as kilopascals. If I'm given a, and we'll see this later, I guess, but if I'm ever given a pressure in bar, when I write it on my state table, I'm going to write it in kilopascals, or I guess megapascals if I can, because then it's really easy when I do P times V, because if I take kilopascals or kilonewtons per meter times V, which is meters cubed, I'll get kilojoules, which is exactly what I want, right? Because I want energy. So here, 101.3 kilonewtons per meter squared times 2 kilograms times this delta V, right? Notice here that this change in specific volume is essentially just V2, because specific volume at 1 is so much smaller that it basically doesn't matter here. I'm going to check my units, right? So because this was meters cubed per kilogram, this specific volume, and I'm dividing by meters squared, I'm left with just meters per kilogram. And kilonewton meters per kilogram is kilojoules. And the kilograms drop out here. So I get a work from 1 to 2 of just under 320 kilojoules. So that's good. That's one of the things that I needed to find. Really, I'm trying to find all 4 of these boxes on my process table, and I found one of them already. Right? To find the total work, I'll need to do the same thing from state 2 to state 3. So I know that as I move from state 2 to state 3, the volume is constant. So if I was drawing this on a PV diagram, I have a vertical line. Right? Now this is a little tricky if you think about this in terms of the calculus. But sometimes we got to think about it in terms of the area under the curve. This is just like when we, some problems will say that pressure is a linear function of volume. And then, you can draw it on a PV diagram and you see that, oh, if I take the area under this curve, it's like a triangle plus a rectangle. In this case, when you have constant volume, a vertical line, there is no area under a vertical line. So we know automatically if we have a constant volume process, that means that the system is not pushing out on the surroundings, and the surroundings are not pushing in to the systems. So there is no work being done if the volume is constant. So work from 2 to 3 is 0. So now we have 2 of the 4 things that we need. So now we can look at the heat transfer in both of our processes. And I'm just going to do these symbolically. So this here, I just rearranged the first law that we had, right? To isolate for Q in the first process and Q in the second process, right? Because it's really delta U is Q minus W. So I move the W's over and now they're positive W, right? And these delta U's are still U at the end of the process minus U at the beginning of the process. So here, I always like to take sort of account of what I know and what I don't know. So I don't know either of the heat transfers, because if I did, then I would be done the problem. I do know the mass, it stays constant. So because I know the mass at one point, I know the mass all the time. I don't know U1, I don't know U2, and I don't know U3. So at this point, I'm starting to think, wow, I'm going to have to fix some states and find specific internal energy. This happens a lot in thermodynamics. We do know, because we just did the previous work, we know the work from 1 to 2, and we know the work from 2 to 3. So I'm at the point of the problem where I have symbolic solutions, and if I could just fix these states and find the specific internal energies, then I'd be finished. Right? So I need to find the specific internal energy at state 1, at state 2, and at state 3. This first one, subcooled liquid, it's funny because maybe a week or two ago, maybe I would think, or I would say, man, I hate working with subcooled liquids because usually it means I have to do this double interpolation thing, which is a huge pain. But now I love subcooled liquids because I have this incompressibility assumption, right? So I'm going to assume that all these properties are the same as if we had the saturated liquid at the same temperature. So here, I'm just going to assume that this subcooled liquid, the specific internal energy is UF at the same temperature, 20 degrees. So here, I would take this table, right? This is the table for saturated water. So this is a two-phase table. I look for 20 degrees. It's in bold over here. And I want UF, the saturated liquid specific internal energy, right? So here I have that value. I can just plug it in on my table, right? So this is 83.95 kilojoules per kilogram. So I've fixed one of my three states. That's pretty good. Now I'm going to move to state 2. This is a two-phase mixture, so I know there'll have to be some quality. I don't know what the quality is. It seems to me like it's probably pretty close to that red line, right? That saturated vapor line when I was drawing my TV and PV diagrams, but I'm not exactly sure, right? So let's figure this out. I know the specific volume, right? And I know that if I knew quality, that the quality at state 2 under the vapor dome would be UF plus X times UG minus UF. Now, that's true for specific internal energy, but it's also true for specific volume, right? So how do we find X in a problem like this? And the answer is we look for some other property where we know what it is. Because right now, right, I'm trying to find specific internal energy, so I've got one equation and two unknowns. So I need another equation. I'm going to use the quality equation for a different property, in this case, specific volume. I'm going to rearrange this to isolate for X, and I see that the quality is V2, that's the one I know, minus VF, divided by VG minus VF, right? Where all of these are at 100 degrees, because now we're looking in the table for this temperature where water's boiling at 1 atmosphere, right? So the temperature is 100 degrees. So I look on the table, right? So I took a snip of it here. I find the row that's 100 degrees, right? I notice that the pressure that's associated, the pressure where we're going to be boiling at 100 degrees, is the pressure that I have in the problem. I know VF, again, about 1 over 1,000, and I know VG. So now I know V2 is 1.57, so from that I can find that the quality is pretty close to 1, right? It's about 0.94. Or if we think about it, that mixture is 94% superheated vapor, so it looks like steam, right? And 6% saturated liquid, right? So it's still some mixture, but we're pretty close to boiling all that water, that liquid water, away. So now that I know quality, which I found from the specific volumes, I can put that back into my equation for specific internal energy, right? So now this X is known, so I can look up UF and UG and UF, or in this case, see, the tables in the textbook don't give us UFG, they only give us HFG, but in this case we have UFG, so that's nice. So we can use that here, and I see that I could do the subtraction myself, 2506.5 minus 418.94, but why spend the time? And I don't know, if you're like me, like I'm really good at putting numbers in my calculator wrong, So here, if they already give me the answer, why do it myself? Right? So this is going to be just about 420 kilojoules per kilogram times 0.94 times UFG. And when I do that, I get a value for U2, 2,373.2 kilojoules per kilogram. Now I'm going to put that into my state table, right? So that's here in red. So now I've got 2 of my 3 specific internal energies. I just need 1 more, right? So now, not surprisingly, right, you might see this on a test too, where we ask you how to find stuff in subcooled liquid region, we ask you how to find stuff in the two-phase region, and now we're going to ask you how to find stuff in the superheated vapor region. Right, so now state 3 is up here in superheated vapor. We know the pressure is 4 bar, and the specific volume is still 1.57. So here, when we're in the superheated vapor region, we're going to have to do some linear interpolation. Now, usually we talked about linear interpolation where you know the temperature and the pressure, and you can use the temperature to find A, and then use A to find the specific internal energy. That's not the case here, right? We don't have the temperature and the pressure. We have the specific volume and the pressure, but the process is still going to be the same, right? So now I got to go and find a superheated vapor table where the pressure is correct, right? 4 bar. This problem doesn't tell you that 4 bar is equal to 0.4 megapascals, so you need to know how to convert units of pressure, right? But this is the right one. Now we see the specific volume is going to be somewhere between, right? It was like 1.57, right? Which is in between 1.469 and 1.584, right? So I can use this information to find A, right? Because I have Vmin on the table, Vmax on the table. I'm somewhere in between here, closer to Vmax, right? 1.57, right? I could draw up and then draw across it if I was solving this graphically, right? But we won't solve it graphically. We'll use math. So we know that A is going to be specific volume at 3 minus Vmin on the table divided by Vmax minus Vmin on the table. And then I'll use that to find A. And when I have A, I'll plug that into my equation for the specific internal energy. So here I have an equation for A. I can put my values in here. I do have to be careful with the units, but at least all the units from the table are the same. So I just have to make sure my specific volume was in meters cubed per kilogram, which it was. And here I get 0.88 as my interpolation factor A. I can put that into my equation for specific internal energy. I know Umin on the table. I know Umax and Umin, or again, I could just find UFG here. Oh, actually, no, I can't because it's not a two-phase mixture, right? So I can't use that shortcut. I have to use Umax minus Umin, right? And then I know that I go 90% of that difference between these two numbers. And in this case, that's 4,234 kilojoules per kilogram. This makes sense to me because it's closer to the higher number than the lower number because my interpolation factor here is almost 90%. So this is good because now I've filled in my state table, right? But what the problem actually asked me for was what's the total heat and what's the total work. I have enough information here to find the total work, but I don't have the total heat yet. So I got to go back to my symbolic solutions for heat transfer. Right? So both of these equations, if you remember, came from the first law, but before we didn't know these specific internal energies, so we kind of took a detour to find those specific internal energies. Now we're in a position where we don't know Q, we do know the mass, we know U1, we know U2, and we know U3, and we know the work. So we have 2 equations and 2 unknowns, which is a good situation to be in. So I can find Q1 and Q2. Now I'm going to put the numbers into my calculator, right? So for Q1, again, I have the mass. I have U2 minus U1. Got to make sure I get the order here correct, right? So be careful with your subscripts. And I have work. I also have to make sure that I have my units right. You know, it could be that when I calculated work, I got an answer in joules instead of kilojoules. But when I'm using the tables, it's always in kilojoules per kilogram. And if I'm multiplying by kilograms here, then I'll get kilojoules. So I got to make sure the units are all right. In this case, they are, so it's not too bad. I add these two together, and I get that 4,895 kilojoules. The other thing I can think about here is that this is a positive number. Remember, heat in is positive. So that means that this is what I expect. I'm adding heat into the system to boil this water, and I'm getting that Q from 1 to 2 is positive. So this is good, right? So this number, who knows if the number is right, but the sign is correct and the units were right. So I feel reasonably confident about that part of the answer. Again, the first law, right? So this is now from state 2 to state 3. I know all of this stuff, so I'm going to put it into my calculator. Hope that I don't sort of make a mistake here. And again, I find a positive value for heat from 2 to 3, which makes sense because I'm adding heat into the system. So now I have 3,722 kilojoules. So I'm doing pretty good here. Both of these numbers for heat made sense because they were positive, right? Heat in is positive from hip to win. Work in is negative, but I got a positive work. So this is work out, which means that the system is doing work on the surroundings, which is true in this case because the water vapor inside of our piston is expanding. And as it expands in this first process, it's pushing that piston out. So that's the work being done by this boiling water is expanding the system. So we are expecting work out here. And if work in is negative, then work out must be positive. So the sign there makes sense too. So the problem actually asked me for the total heat, right? So I add these two numbers together and I get that the total heat is 8,617 kilojoules. The total work is really just the work from the first process because the work from the second process is 0. So that's 320 kilojoules. Notice in this case that the heat transfer is much higher than the work, right? Again, we can look for validation. We check the units throughout our equations, and they made sense. We got units that we were expecting, right? So you do actually have to carry units here, right? And we only used incompressible assumptions for fluids. So we thought about the assumptions that we made, right? We didn't make the incompressible assumption when we had a two-phase mixture or a superheated vapor. So, you know, we were reasonable with the assumptions that we chose. We checked our signs and they make physical sense. So that's the end of this problem. This is the kind of problem that you'll probably see in the homework this week. And it's certainly the type of problem that you might see on a midterm exam for the first part of the class here that we're just finishing up. So that concludes what I wanted to talk about today. I'm happy to go over any questions that you might have.
I have one quick question.
Shoot.
What did the assumption for incompressible liquids give us?
Sure. So that was, remember when we assumed that the specific internal energy and the specific volume for the subcooled liquid was the same as the saturated liquid of the same temperature? That assumption is only valid when you have an incompressible liquid. Right? So another way to sort of apply that same type of assumption or another assumption that you might get if you're assuming that a liquid is incompressible is that you would say that delta U is equal to Cp times delta T, or Cv times delta T, I'm sorry. So those are both assumptions that are associated with assuming that the fluid is incompressible.
Thank you.
I thought there was another question as well. Matt.
Yeah, I had a quick question. So what will the multiple choice on the midterms look like? Kind of similar to how the quizzes were, or are they going to be more in-depth?
Yeah, I think they'll be pretty similar to the quizzes. So they'll probably be broken down close to 50-50, where maybe half of them are sort of more definitional type questions, and half of them are involve some math. But typically you'd see in a multiple choice type question, maybe there's one calculation that you have to do as opposed to, 3 or 4 calculations that you'd chain together in a long answer type problem.
And will this lecture be uploaded like the rest of them so we can kind of watch back how you went over the problem?
Yep, I will do that. So first there is the sort of non-live version of the lecture is already uploaded, but right after lecture, it takes a little while to process the video, but I intend to put it up tonight or tomorrow morning.
Okay, sounds good. Thank you.
And that'll be true too. So next class, we'll do a review for about half the time, and then we'll do a... So you need to know how to use the first law when the fluid in the system is something like water that changes phase. But you also need to know how to use the first law when the fluid in the system is an ideal gas. So next class, we'll do review for about half the lecture, and then we'll do an example where the working fluid is an ideal gas. So again, the sort of asynchronous version, I guess, of that video is already up if you'd like to look for it. And I actually split apart, so I have the whole lecture, but then I also have just the problem. So you're welcome to look at that too. That should be lecture 12 in this week's content. But I'll put the live version of that up as soon as I can after Wednesday's class as well. Do we have other questions? All right, everyone, thank you for your time, and I will see you on Wednesday.